In this problem, we're given a bandpass filter, and we have to sketch the magnitude characteristic of the Bode plot for GV of J omega. Okay, GV of J omega would be V0 J omega over Vs J omega. And if we look at our circuit in the frequency domain, I've just got it written in terms of L, C, and R. In the text, we've got the transfer function derived. So it turns out to be R over R plus J omega L minus 1 over omega C. And we can also write this as J omega times R over L over J omega squared plus J omega R over L plus 1 over LC. Okay, so if we notice, we've got simple 0 at the origin. We've got a set of quadratic poles. Okay, so a couple things we need. First is the resonant frequency. Okay, so if we look back at our circuit here, the resonant frequency is 1 over the square root of LC. So we have 1 over the square root of 1 times 10 to the minus 6. So our resonant frequency is 1,000 radians per second. Now let's calculate the two half-power frequencies. So, for instance, one of them from the textbook is minus R over L plus the square root of R over L squared plus 4 omega naught squared over 2. And if we go through and calculate, we have 1,000 over 1 plus the square root of 1,000 squared plus 4 times 1,000 squared over 2. So we have a minus 1,000 plus 2236 over 2, and that tells us that one of them is at 618 radians per second. And then the higher half power frequency, we have plus R over L plus the square root of R over L squared plus 4 omega 0 squared over 2. And it turns out to be 1618 radians per second. So here's our two half-power frequencies. We've got our resonant frequency. So now let's sketch the characteristic. So let's first label our frequencies. Here's 1,000, 1618, 618. Okay, now if we look at our transfer function, okay, we can see we have a simple 0 at the origin. And another thing is, if we'll remember, here are our two half-power frequencies. And at that point, we're going to have a gain of minus 3 dB at both of those points. And if we look at our transfer function, you say, well, what's the gain at resonance? Well, at resonance, these two terms would cancel out, so the gain is 1. So in dB terms, that's 0. So we know at the two half-power frequencies that we're at minus 3. We know at the resonant frequency that we'd be 0. So if we start off, here's from our simple 0 to origin, that would be a slope of 20 dB per decade. one of the poles turns on at 618, and it has a slope of minus 20 dB per decade. So what's going to happen is it's going to give us a slope of 0 until we get to the other pole. When it turns on, then we're going to go down at a slope of minus 20 dB per decade. Okay. So ideally, this would go right into 0 there. So this is our sketch and our magnitude. So here's a simple 0 to origin, slope of 20 dB per decade. First pole, omega low, we turn on here. We're at minus 3 dB. That gives us a gain. We hold steady at minus 3 dB. Then the other pole turns on at 1618. We go down at minus 20 dB per decade.